All right. Cool. All right, how's everyone? Doing all right? Good. Week number 4? It's 4? Somewhere around there. Okay. So there were some quizzes over the weekend. Hopefully everyone enjoyed sleeping in at least one day, at least a little bit. Also an assignment uploaded. It's not due until next week. And you can get me this a couple different ways. You can bring it into class on Thursday if you're here, or possibly next Tuesday. I think I said the due date for next Tuesday. Or you can scan it and email it to me. I'll also put a link up to where you can scan it and upload it to Blackboard as well. So somehow, somebody can get it to me. Then I guess you don't really necessarily have to scan it. I would prefer a scan, but if you don't have a scanner, that's fine. A picture would suffice. There's just some questions here relating anywhere from chapters 1 through 4. A little bit of calculations down here, 6 or 7. And somewhat of a drawing calculation here on number 2, as well as a little bit of a drawing on number 1. So it is up there on Blackboard available. Any questions on that? We'll go ahead and get started with chapter 5. Things are moving. All right, torques and sure everything looks good there. Okay. Torques and moments of force, maintaining equilibrium or changing angular motion. So a lot of the motions we've looked at so far are linear, so going somewhat in a straight line, maybe a curvilinear fashion, but this one is going to be specifically looking at the angles and changing rotational direction and the forces that are at work during this. So the definition of torque. So this is a turning effect produced by a force. Fairly simple. Also can be described as a moment of force or just simply a moment in the physics world. Centric force. Excuse me. Centric force is some sort of force from the outside, an external force, that is going to be directed through what is known as the center of gravity of the object. We'll touch on a little more specifics about the center of gravity in next chapter, actually. When this force acts on the center of gravity, it's going to cause a linear motion. So the centric force going through the center of gravity causing some sort of linear motion. An eccentric force, not to necessarily be confused with the eccentric contraction of muscle, but an eccentric force is that force that is not applied, not directed, not applied through the center of gravity of that particular object. So this is what's going to change the linear and angular motions. There's going to be some rotational movement that's going to be occurring. Very simplistic example of the centric versus eccentric forces. If you have a book on your desk, for those of you at home in your dorms, wherever you may be, you probably do this as well. You can try to push that book forward, and at some point you're going to find a spot where it moves just simply in a linear motion, and it will not rotate. So that would be the centric force. Now, if you take one of the corners and start to push forward, then it's going to start to spin, and that would be the eccentric force that you're applying. So that was looking at just one force being applied, but applied more than one force to the objects, and that would be a force couple, since there's more than one, at least two. They're married. They love each other. Well, maybe they're just dating, thinking about getting serious, wanting to maybe move in with one another. So a pair of forces that are going to be acting in equal but opposite directions. So we can also use a vector in these cases, and each one of these two arrows are going to be acting in opposite directions. And we can actually use the textbook example again with this. The example with pushing a textbook on the table. So we're causing a change only in the angular motion of the object, and the resultant forces, or the resultant of the two forces that are going to be acting equal and opposite of one another is going to equal 0. Meaning we're going to have some type of rotation on an axis. As example with the textbook. Ah, it's like I knew. It's like I knew. So pushing it straight forward to the center of gravity. Oh, that's about as straight a line as I think I've ever wrote on it. And if you take a corner and move it one direction, it's going to cause some spin, but also maybe a little bit of forward motion. Some of that also depends upon the frictional forces between the surface of the table and the book itself, but we'll just say it moves forward a little bit, but also some rotational forces off the center of gravity. But then if we take both hands and push both corners in equal opposite directions, then we're going to have a resultant of 0 of that force couple, and we're going to have rotation of the book then. So we either have linear with the centric, linear plus angular with the eccentric, and then with the force couple, we will have just angular motion. The mathematical definition of torque, and this is where it gets somewhat important when we look at the human body, the attachments of the muscles, and also maybe some tools that we use in daily life, in some work environments, in sports. So it's a turning effect produced by the force and the distance between the line of action of that force and the axis of rotation. Sounds confusing. Sounds like a Jeopardy question. This is the turning effect produced by the force, and this is line of action of the force and the axis of rotation. This creates a distance that we can measure, and that distance becomes very, very important in the calculation. That distance is the moment arm. So it is the perpendicular distance between the line of action and the line parallel to it that passes through the axis of rotation. Maybe more confusing than the mathematical definition. Okay. So here it is in a nice, beautiful little picture. So we have force moving in one direction. Notice this is an eccentric type of force. And then we also have, oh my goodness, a parallel line that is running through the axis of rotation. So parallel to where that force, the direction of that force. And then we have the distance between those two parallel lines. That's the moment arm. The longer that moment arm, the better we're going to be able to cause torque a little bit easier. And we can take advantage of this principle in a lot of different scenarios. It has many implications in athletics and just human movement in general. This is one of the reasons why we have weaknesses in certain locations of range of motion in all of our joints. We'll see an example of that here in a little bit. So looking at it from a mathematical equation, we have T, which is torque, or the moment of force that's being applied, is going to be equal to Fr. And the F is the force itself, usually measured in newtons. Could be measured in pounds. Could be kilograms, I guess. Usually pounds and newtons, two very common units. And then the moment arm itself, measured in meters, sometimes centimeters, could be inches. Could be feet. Inches, centimeters, did I forget one? I mean, you could, as long as you just kept it consistent, you could use any unit length that you want. Miles, light years. So common units for torque would be Newton meters, Newton centimeters. Other ones that we might use or you might see, foot pounds. So again, that R is just simply the distance between the parallel lines of the force and the perpendicular line to that force running through the axis of rotation. So fairly simple equation. So not a lot of stuff to go wrong there. As long as we know what the force is, what the distance between the parallel lines is, or if we're trying to find one of those, if we already have torque, just use some algebraic manipulation and we're good to go. Vector quantity. So just like the vectors that we see before, we're looking at a size and the direction description in this case. So there's a turning effect around a specific axis that came from. So there's a specific direction that it's going. And counterclockwise torques are seen to be positive, and clockwise torques are negative. So let's see if we can outline this. I'll go around this way. It's the negative. This is also another example. One second. Another example of your actual view on the object. Because if something is spinning clockwise, if you're looking at it, say from the top, then if you look at it from the bottom, it's now spinning counterclockwise. So orientation is going to make a big difference here. But as long as you're consistent throughout the entire explanation of how that object is rotating, and there might be standards in certain scenarios that you may have. So torques acting about the same axis may be added or subtracted to determine the resultant force that is being applied in that case. So if they're acting in the same direction, they can be added. If they're acting in opposite directions, they can be subtracted, and we can get a resultant force and determine what the total amount of force is, and what that will determine what direction then the object may be moving, or rotating in this case. Any questions so far? Nothing in the chat. Good. All right. Talk about torque. You got probably one of the most obvious examples that we use probably every day, as long as you live or are in some type of building or get in a car some way, somehow. I mean, other than just being in our bodies somewhere also, but something we use pretty much every day. We don't even think about it. You wonder what that is? What object that might be? I mean, there's probably plenty of them. One that I'm thinking of is a door. Doors are a perfect example of torque. And the way they're designed is to try to maximize the torque that we can apply to the door. So why are doorknobs located on the opposite side of the door, of the hinges? Why aren't they right up against the hinges? Why aren't they right in the middle? Every once in a while, excuse me, you'll see a door that has the handle in the middle. Sometimes those are somewhat decorative and but have you ever thought if it's a push door, if you're pushing one way, you ever think that the hinges were on one side, but they were actually on the opposite side? So then you go to the side that is actually the hinges and then try to push it. It takes a lot of force to open that door then. Usually what happens is you correct it and slide over a little bit and start pushing away from the hinges. So you've increased what? Yeah, you've increased the moment arm. You're applying a little bit more torque now. You maybe apply the same amount of force, but the torque is now increased. So if we look at the top, say we've got the hinges, then we've got the door. The door handle should be somewhere in here. And we're applying force to the door handle. And we got that parallel line running through the hinges. So now we have the distance between those two lines, which is R, or the moment arm. The further that door handle is away, the more torque you're going to be able to apply if you apply the same amount of force. The other way you can apply more torque is just apply more force in general, no matter where the handle is. But to start to equal it out, to get the same amount of torque, it's going to take a little bit more force, especially once you get really close to the door hinges. So therefore, large force and a small moment arm is going to be equal to a small force and a large moment arm, just based upon the equation calculations. So this simple example in our daily lives, the door, the limitations that we're able to exert, somewhat limitations. We try to use this mathematical principle to make it a little bit more efficient to open doors. So we use larger moment arms when we want to create greater torques. Also a case where we have other forces at work with the door too. Probably the biggest one being friction. What are the door hinges made out of? Is it touching the floor? Is it touching some type of carpet? Is it an old rusty hinge? Was it just lubricated? What type of lubrication is on it? But all things being equal, larger moment arm is better for torque. What are some other common tools maybe that we use that have the same principle? We have a line of force, we have some sort of rotational action that's occurring, and then we create a moment arm based upon those two lines. Any tools that you might use? Breaker bar. Perfect example. Can you describe a breaker bar?
A long piece of metal to break open a bolt.
Yeah, exactly. So, those of you online, Gavin said the shovel also, good example, perfect example. Breaker bar was an example here, which was just you're increasing the distance between the rotation, which is where the bolt is that's stuck, and you now basically have this big bar that's attached to maybe a wrench, and you're just creating more torque. Sometimes you can create more torque also by taking that breaker bar and standing on it and applying more force that way. But increasing the moment arm, that's one example that we use. Even some smaller objects, shovels, definitely a good one. Common tools, a hammer, even clothes clips, clothesline clips, what they're called. So we have the force. Force in this case, we have actually two forces, and we have the axis of rotation. So in this case, with the ones that have two, like the pliers, we're actually going to have two moment arms being applied. Trying to draw it the best you can here. Found out drawing on the board in here doesn't necessarily work for you guys online. Wheelbarrow. Yes, a wheelbarrow is another perfect example. In fact, a wheelbarrow is also a perfect example of a certain type of lever in the body. I believe it's the only of this type. Another Jeopardy question. A wrench or breaker bar, if you need a little bit more torque for that. Stapler, for example. And then other common ones, we already mentioned the shovel, in this case. So we have the axis of rotation would be the backhand, and then the forward hand is going to be pulling upward. So we have these two lines that are parallel, and the distance between there would be the moment arm. So in that case, with the shovel, how would you create more torque if you applied the same amount of force?
Move your hand down.
What's that?
Move your hand down.
Yeah, move your hand down. Move your front arm down. You've increased the moment arm, and you're going to be applying more torque that way. Same thing with the wheelbarrow. You get a longer wheelbarrow, I guess, if you wanted to, or grab the handles further back. Then we have the other example there of the nutcracker. In this case, with the nutcracker, we actually have a unique scenario where the axis of rotation is actually towards the end, and we have two separate parallel lines that are occurring here. So we got one moment arm here, and we got another one that is here. All right, I think we've beat moment arms to death. So, then start looking at the muscles and the torque within the muscles. So the same principles being applied inside of the body could also be applied outside of the body too. Torque. So the line of action of the force of muscle force is the distance from the joint axis. Basically where the attachment point is of that muscle. Look at it as the insertion. So then torque then is going to be produced by the muscle on the distal limb, the insertion. And it will tend to rotate the limb in one direction about the axis of rotation, which is the joint in this case. Simple example would be the bicep. So we have a muscle force right there, and the axis of rotation is simply the elbow. Now we have the two parallel lines, and we have it's supposed to be a smart board, but sometimes I doubt that. And then we end up having an R, creating a moment arm. The one thing that amazes me about this is that this distance is not very far. If you really look at it from an anatomical position or scenario, I don't want to say position because then it gets confusing. From an anatomical standpoint, it's not very far, but we're still able to produce a lot of torque, which means the force the muscles are generating is quite a bit. And there's really no way to increase this significantly. We'll increase it or decrease it a little bit. We'll see that. But we can't increase it by just changing the insertion like we would with a door, increasing the distance between the door handle and the hinges. You know, we can't just simply move our insertion of the bicep to somewhere else, or, you know, up near the wrist. That would be pretty cool. So we have this smaller mowing arm, and it will change at least a little bit throughout the motion. In fact, so what happens, the torque on the forearm produced by biceps as you're moving from full extension to 90 degrees. In fact, you can feel this. If you pinch your elbow, you guys can see my line, just pinch your elbow, just take your, and just start flexing. You can kind of feel that distance between your finger and your thumb increase and decrease as you're moving along. So therefore, if we're changing the moment arm depending upon the angle of the joint, we're going to be changing the torque that's going to be applied. So when it is extended, such as in that scenario, axis of rotation is not going to change. You have a shorter moment arm versus if we are at about 90 degrees, we now have a longer moment arm. In this scenario, because we've increased the distance between the insertion or the line of action of the force and the axis of rotation. So in terms of biomechanical efficiency, about 90 degrees is where we're going to have the maximal amount of torque within this particular exercise, this particular movement. Now, there's another thing here that's going to determine the weak point or the strong point within an exercise like the bicep curl as well. And it has to do with the properties of the muscle itself. A slightly stretched muscle is able to produce a little bit more force, but in combination with this principle of torque, it's about 90 degrees. It's actually maybe a little bit further than 90 degrees because we need to stretch the muscle a little bit more. So the strong point within this action is going to be roughly, maybe not 100 degrees, but pretty close to 100 degrees, maybe a little bit further than 90, between 95 and 100 degrees. You need to slightly stretch the muscle for the properties of increasing muscular force, but also in relation to the torque as well. But this is a key component to determining where that efficiency is in that strong point within that movement. Another slide on this. So can the muscle create the same torque throughout this range of motion? No. I mean, if you're applying the same amount of force throughout the entire range of motion, you're going to change the torque because you're changing the moment arm. So if the force, or the F portion of that equation, is remaining constant and the moment arm is changing throughout the motion, then the torque is going to change. At the bottom, it's going to be lower. 90 degrees, it's going to be higher. And then as we contract even further and make it an acute angle now, it will start to decrease again. Once we get past the 90 degrees, it's going to start to shorten once again. So changing the angle at the joint, so you're changing the moment arm, and partially explains why muscles are apparently stronger in some positions, some joint angles, than in others. And you can feel this too if you're lifting something. It could be a barbell, dumbbell, it could be, I mean, anything. Once you get it past fully extended, it feels like it starts to become a little bit easier to lift that weight. Then once you get to a certain point, it feels maybe a little bit harder again, because you're increasing the moment arm, increasing the moment arm, increasing it, and then now you're starting to decrease it, decrease it, decrease it. And part of the reason why, at least in the bicep curl, that example, there is a sticking point past the 90 degrees, getting closer to maybe 70, 60 degrees-ish. The moment arm starts getting shorter and shorter. The other part of that is the properties of the muscle. A very shortened muscle, a contracted muscle, is going to produce less force. Nope, there we go. That's the picture again. Any questions on this so far? Any in-person, online gallery? And that picture again. So looking at the dumbbell curl again, keeping with this example. Because it is Tuesday, it'd probably be arm day for most people, so I guess it's pertinent. So the dumbbell doesn't get heavier, it's just the torque gets a little bit less once we get past 90 degrees, but as going from extended to the 90 degrees, it lengthens, so the torque gets a little bit greater. right. Any questions? 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 So it's looking specifically at the free weights, torques that are produced by the weights, your arm, you're going to vary because of the change in the moment arm. It's not necessarily because the weight actually changes. And I say that because I've heard high school coaches say that the weight changes as you move through the motion. And they mean that in a literal sense. It's kind of ask them about it. Oh no, it changes. It has to do with gravity, and thought maybe they're going to mention swamp gas from Venus or something like that. Which, by the way, did you see that there's life on Venus, or there's potential life on Venus? You see that? Yeah, that's awesome. Yeah. Might not be intelligent, but it could be some life, I guess. Probably microbial life on a lot of places. Don't know. Anyway. And there was the picture again of the bicep and the moment arm forces line of action. So this principle of torque is used could be used a little bit in some other scenarios in training in different various machines, such as maybe leg extension machine. At the bottom, you're starting off this exercise, the moment arm is going to be larger. So the axis of rotation isn't going to change. It is going to be the knee, in this case, right there. And then the line of action is where the line where the force is being applied is going to be where the pads are. You put on the legs or the feet. So thus increasing that distance. Some of these machines you can actually adjust how far that distance is from the pad to the knee. So increasing it is going to give a little bit more torque. But also, from a mechanical standpoint, the closer and closer we get to fully extended in this case, there's going to be less torque that's going to be applied. Even though it's the same amount of force, the weight stack didn't change. That moment arm has now decreased. And it's going to feel like it's maybe a little heavier up towards the top than it was down at the bottom at the start of the exercise. And that's just based upon where the pulley was too. So, because the pulley was right there if you have it. So maybe changing where the pulley is located could maybe cause a little bit more of an advantage. Maybe a redesign of this machine because a little bit more torque being applied. And then you start getting into some of the principles with pulleys and stuff like that too, which we're not going to get into. And what the material what the material is here. Is it rope? Is it maybe covered wire? What gauge of cable is it? A couple different examples I'll give of that. This is kind of a side note to this with differences in machine designs, weight training machine designs. The leg extension machine that we had at our high school, it was something similar to this. It was maybe a little bit more compact this way, so your back was basically almost right up against the weight stack. But there was this cable that kept having to be replaced. I mean, every I don't know, month and a half, we had to go get a new cable cut and put it on there. It just kept breaking. And it was probably, I don't know, a ½ inch thick. And we're like, why is this thing breaking so much? Somebody smart finally entered the weight room the one day and said, you got too thick of a cable. Every time you're moving that thing, the thickness is causing it to keep bending. And that's causing stress throughout that entire length of the cable. So then the little strands just kept popping, and then, you know, we'd always be tough guys and be like, I want to pop it today. So you put as much weight on it as possible, and yeah, anyway. Yeah. At Kent, the weight training class I taught, the machines that we had actually had chains, like they looked like bicycle chains, and you had to oil them. If you didn't oil them frequently, at least once a week, man, it was hard. They would dry out, and the frictional forces would just be too much, and the weight, if you tried to say it was 50 pounds, it was probably more equal to like 70 pounds. It was that much resistance. So, and that's just the difference in the design over the years. Anyway, just a weird side note that probably doesn't make any difference in your lives, but there you go. All right, let's move on. Questions on that? All right, net torque. So torques that act around the same axis. So you're summing the torques that act on an object. The book gave an example of pennies, at least on an eraser. So the eraser would be the thing right here, the object in the middle. And say there was a ruler that was placed on top of that eraser, then we just place pennies on either side. A certain amount of pennies, could be coins, whatever it is. And that's going to cause different forces on either side and cause some rotational actions. Eccentric forces. So we can simply just look at the different torques of each one of these weights or pennies that's applying to this. And we got the distances pretty easy if it was a ruler. You can see the distance, and as long as you know how much the penny weighed. In this case, we're just looking at 1 penny, 2 penny. So the pennies placed in the left eraser, left of the eraser, are going to cause counterclockwise rotation, which is seen as positive torque. So we need to have orientation in this case, so that we know what's positive, what's negative. We can't just say that all of it's positive or all of it's negative. So if we're going, sorry guys, if we're going this way, we got positive. If we're going this way, we got negative. So everything to the right then is going to be causing negative torque. Oh, we got visitors. I think I have. Whoa. 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 Whoops. Sorry, guys. So on the left side, let's add these up. On the left side, well, what do we got? We got 1 penny. Penny is going to be the unit as well. We have 1 negative penny. And it's also to the left side. And when we look at directions, we generally say left is going to be negative and the right is going to be positive. So the distance in this case is not just 5 inches, but negative 5 inches away. And that is going to be the torque for this. So that negative 1p, that was the F, and the negative 5 was the R, or the moment arm in this case. If you do the same for this one, it would end up being negative, or excuse me, positive 1 penny times 2, plus 2. And then the same thing with the other one, positive 1 penny times positive 3. So when we map this out, we have negative 5. We have a positive 2, and we have a positive 3. So we have negative 5 on this side, remember, plus 2 plus 3, and this is actually going to be equal to the net torque. So what is negative 5 plus 2 plus 3? Everybody online? Calculate it up. Negative 2 plus 5 plus 3 should be 0. So in this case, nothing's going to happen. It's going to balance out, if you will. 2 torques on either side are equal, so we balance it out. Okay. Maybe that was a boring example. Whoa. Whoa. I forgot where I was going with that. All right. So how much torque is created? About the elbow joint while holding a 20-pound dumbbell. And the elbow is flexed at 90 degrees. If the length of the forearm is 12 inches. What do you think? What would be the number? So we're trying to find the torque. We got a 20-pound dumbbell. 20-pound dumbbell is pressing down here. There's the dumbbell. The axis of rotation, which was this point right here, is the elbow. And we have a distance of the arm to where that weight is being pressed down. So we have the two different lines that are now created. Let's try to get a different, let's do, I'm not sure what we'll contrast. Let's do that. Okay. So the two different lines, oh, there we go. They're created. They're going to give us the R, which we already know, which was 12 inches. But it's a positive 12 inches because in this case we're looking going to the right. Again, if you were looking at it from the opposite side, it would be negative. But in this scenario, we are positive 12 inches. And what about the dumbbell? 20 pounds. What type of rotational force is it causing? Is it clockwise or counterclockwise? What would it cause? It's pressing down this way. It's likely to cause a clockwise rotation, which would be negative. That's where we're going to have the negative 20 pounds in this case. So if we take the force, negative 20 times the R, which is 12 inches, we got 20 times negative 20 times 12. Write it down. Well, positive 12. We got 240. But remember, it is negative in this case. And the units, pounds per inch, or pound inches, or inch pounds, if you will. So that would be the total torque in a negative direction in this case. Because it is clockwise. It's of the clock and it's wise. Questions on this? Yes, no? And another example, what force must the muscles produce to generate sufficient force, torque, sufficient torque to hold the dumbbell from the previous example? If the point of insertion is 1 inch from the axis of rotation, which is the elbow, So we can take the, oh my goodness. Take the net torques that is necessary, and from that last example, what do we have? Negative 240. Oh my goodness. We have the negative 240 plus we're trying to find what? We are trying to find the force. I believe there were a bunch of movies that we're trying to figure out. I don't know. I've never seen Star Wars, so I have no idea. I'll be honest. I know I'm like one of the 3 people that have never seen Star Wars. Oh my goodness. So we're trying to find the force. So in this portion, we don't know the force, but we do know the distance from the force being applied by the biceps to the axis of rotation. And that distance is going to be, in this case, what was that? 1 inch. And because that line of action of the bicep is causing rotation this way, let's see if you guys see it online, this way. So counterclockwise, in this case, that 1 is going to be positive. So we got a positive 1 inch. And this should equal 0 because we just want it to hold it there. There's no movement. And back to Newton's laws, there's no movement in this case. So what do we have? Do we want to figure this out? Oh boy. Oh boy. What's your gut telling you? You need to oppose the force and counteract what is happening on the one side, dumbbell. The bicep needs to react and create a torque that is less than, equal to, greater than. Equal to, there we go. Okay, good. Maybe we'll come back to this next time and get it. So when you mathematically and algebraically figure this out, it then should equal the 240 that is necessary to counteract this torque in the positive direction, counterclockwise. Thus, proving Newton's first law, just by simply calculating a couple numbers together. So, anyway, any questions? Maybe look at this again. Thursday, I think that was, oh, I guess I'm going to center of gravity. We'll start center of gravity later. We'll start on Tuesday, or Thursday. I think this is Tuesday. So we'll finish this up on Thursday. Probably get through most of chapter 6, if not all of it, and then there we go. So probably start more quizzes and everything on probably Thursday, Friday-ish. So we're getting through pretty quickly. If you have any questions, let me know. If not, thanks for playing. Have a good rest of your day. Bye, everybody online.